Hi, so in this video, we're gonna work on section 3.4. And in section 3.4, we're gonna develop the 5-number summary and then the graphical representation of the 5-number summary box plots. All right, so I'm gonna start off just looking at some data that I have presented to you in the notes. And this data here is collected by a group of Brigham Young University, Idaho students. They collected data on the speed of vehicles traveling through a construction zone where the posted speed limit was 25 miles per hour, okay? And these are 14 speeds that were collected. And notice that I already have ordered the data. So it's from the slowest car to the fastest car. All right. So what I want to do is think about the idea of the median and introduce a new idea of quartiles. So we know that the median is the middle data point. It's what we would get if we would break the data into two equal sized groups. And so I'd like to think about my data here as placing the ordered data onto, perhaps this is like a lasagna noodle, right? And each data point is equally spaced out, approximately, right? And so what we're going to do is we're going to break this noodle into two and try to make the same number of data points on each of the noodles, okay? And that's going to be our median. All right, so we've done median before, and we just want to, I just want to review it. So we know that n is equal to 14. Yeah, 14, and so the location of the median is n plus 1 over 2, 14 plus 1 over 2. The location of the median is 7.5, so the median is going to be between the 7th and the 8th data point. So let's go over here to our lasagna noodle and break it in two. 1, 2, 3, 4, 5, 6, 7. Okay, so my median is going to be the average of 32 and 33, 32.5. Okay, here, right in the middle. So quartiles are divide a data set into 4 equal parts. We notice the median divides the data set into 2 equal parts. So this is just, quartiles are like an extension of median. Okay, and so we're gonna break this noodle again here, and we're gonna break it over there. So when we break the noodle here, it's gonna be Q1 or first quartile. The median is called Q2 or the second quartile. And then we'll break this sub data set over here into 2, and that place where we break it is Q3 or the third quartile. Okay, so to find the first quartile, we want to look at the sub data set to the left of the median. And how many data points are in that data set? There are 7 points in our sub data set. Right, so our little sub data set has n equals 7. N plus 1 over 2 is 7 plus 1 over 2, 8 over 2, or 4. So 1, 2, 3, 4. This value right here is our first quartile. We'll call it Q1. And now to find median is the second quartile. And to find the third quartile, we're going to go over to the sub data set to the right of the median, break it in half. Okay, and so this data set, by design, should have the same number of data points as the original data set, okay? I mean, sorry, as the data set to the left, right? So the data set to the right has 7 points, and the data set to the left has 7 points. So my median, the median of my sub data set to the right of the median is going, we're going to count into 4. 1, 2, 3, 4. So this guy right here, that is my third quartile. Okay. All right. So we have the quartiles. Q1 is 28. Q2 is 32.5, and Q3 is 38. So we have a few concepts and a little bit of terminology to think about. What we're going to think about first is the data that's between Q1 and Q3. We call that the interquartile data. So let's bring it down. So this data here, all of this data, this is the interquartile data, right? And what we also have is another measure of, remember I promised you we would have a third measure of variability. And the third measure of variability is the interquartile range. Interquartile range is equal to Q3 minus Q1. And in this case, that's 38 minus 28, or 10. So the interquartile range is 10. That's going to be our third measure of variability. So we had the range. We could look at this data and find the range. 40 minus 20, that's 20. We had the standard deviation, which I assure you, I cannot look at this data and just tell you what the standard deviation is. That's quite a bit of calculation. But then you get the interquartile range, which is also a quickie in terms of calculation. So if you needed to get an idea of variability in a data set and time was tight, you might lean on range and interquartile range. All right, so these three numbers give us a lot of information about the data. So we know, for example, that 25% of the data is between the minimum 20 and Q1, right? And 25% of the data is between Q1 and Q2, and 25% in each of these little 4 chunks. It's probably worth my mentioning that this idea of quartiles and exactly how they are calculated when you're coming in between 2 points. It might vary a little bit from software system to software system, but we're gonna do it like this. We're gonna consider when we need to find a quartile, and if the location of the quartile is not smack on a data point, that we average the 2 data points. All right, but you might find it different on your TI calculators, or there'll be a number of different software systems you might play around with, not just for this course, but if you have data in another class. And they might vary just a little bit, but not enough to worry. So we're just gonna kind of go with that. Okay, so we're gonna put together some information here. It's gonna be the 5-number summary. And the 5-number summary is a list of numbers, the minimum, Q1, Q2, Q3, and the max. All right, so we get used to seeing 5-number summaries, and let's go ahead and write out the 5-number summary for this speeding data, right? So it's 20 is the minimum, 28, 32.5, 38, and 40. So that's our 5-number summary. 5-number summaries are great because they're fast and cheap, right, to calculate. You can calculate them pretty easily. If you can get to that ordered data set, Stem and Leaf can help you with that, okay? And we see that if we look at this data set, at this 5-number summary, we see a measure of center, we see the median. We can subtract the max from the min pretty easily and get the range. And we can also find the interquartile range, or the range of the interquartile data. So that the middle 50% of the data, 38 minus 20 is 10. Okay, so I now want to draw, introduce a graphical display called the box plot. And this is something that likely you would have seen if you maybe went to school in Massachusetts for middle school. You might have run into this, this graphical display. Okay, so we're going to draw an axis that's going to be big enough to go from the minimum to the maximum. So here we go, 20, 30, 35, and 40. All right, and we're gonna dot each of the numbers in the 5-number summary. So we have a 20, we have 28, 32.5, so right between 30 and 35, and 38, and 40, maybe 38's a little over here. Okay, so the box plot draws a box around the interquartile data, so from Q1 to Q3, and this is just the box here, and the height of the box doesn't really mean anything. So it could be a little narrower if you need it to be, or it could be a little wider, but it doesn't matter. We're going to do a bar at the median, and this is the whisker. So from the minimum to your Q1 and from Q3 to the maximum. This is called the box plot. And again, you can look at it, you can see a measure of center and 2 different measures of spread. All right, so now suppose a 15th car comes through this construction zone. And the going really fast, okay? Suppose this car is 100 miles an hour. I'm gonna just put him in red so we remember that he's who we're adding. So let's go ahead and put him there. So I would like to understand how this, well, we'll call him an outlier because his speed is certainly different than all the other speeds in the data set, right? So he is outside the pattern of the data. So how does this outlier, how does the outlier affect our measures, right? So we've been working with, in chapter 3, measures of center, mean, median, mode, measures of variability, range and standard deviation, interquartile range, right? So how do each of these react or respond to an outlier situation? Okay, so I am gonna just share my screen, and we're gonna look at the notes because I have already done some of these calculations for us. So looking at the notes, I think that it's probably worth my making a comment is that if I'd like to compare the two distributions, so above here, this is the distribution of the original data, and below is the histogram of the data with the new outlying data point. If I want to actually compare the two distributions, it's much easier to see the comparison if we keep the horizontal axis, the scale on the axis the same. So I can see here, I can see here the two distributions at the same time, and I know that they're the same except for this data point over here. Okay, so just a graphical guideline for when you're trying to compare distributions to keep the axis the same. All right, and I made a table here of the mean and the median, some numerical measures, right? With the 15th car and without the 15th car. So I'm not going to go through the calculation of all of them, but I just want to sort of look at the numbers and see which of these measures are reactive to the outlier and which of these measures are resistant to the outlier. So when Mr. 15th speed demon comes in, right, the mean goes from 32.1 miles per hour to 36.7 miles per hour. One car changes that, the average, the mean miles per hour by more than 5. So the mean is quite reactive to that outlier. On the other hand, the median, because the median is only concerned with the data in the center of the distribution, that the median does go up. It goes up from 32.5 to 33. The median would have gone up in that same way had the 15th car been coming in at 50 miles an hour or at 100 miles an hour. Because the median only really cares about the ordering of the data and what's going on in the center. Standard deviation, think about the length of that green bar associated with Mr. 100 miles per hour, right? So you're averaging how far on average observations are from the mean. That's your standard deviation. So because of that, the standard deviation is going to be reactive to the outlier. So we're going to have this one really big long green bar, and those lengths of those bars get averaged in our special standard deviation way. And we end up with a standard deviation that's increased almost 3 times as much just because of that one point. Interquartile range, on the other hand, not really. That does not care. Really, interquartile range is similar to your median in that, yeah, I'm looking at what's going on in the center of the data. So the interquartile range just goes from 10 miles per hour to 11 miles per hour. And the range itself is very reactive because it's max minus min. So the range goes from 20 to 80. So just something to think about when you consider measures, how reactive each of the measures are to the to an outlier. Okay, so we're going to come back and let's see. I'm going to stop sharing. Okay. And I'm going to end the video here, and we'll take it up one final video to wrap up chapter 3.